Hello, this is our review of Chapter 11. It's a continuation of the previous two chapters. In Chapter 9, we compare the look and feel of the prior period data to the look and feel of the current data using descriptive statistics. In Chapter 10, we quantified the change from one period to the next, but for each line item, we did need a before and after reading. And that was rather clever. We made some use of analytic geometry. What we're doing now is we are looking at the past pattern, the past time series of, it could be revenue, expense, loss type numbers, and we will be projecting forward, and then we will compare the actual to the projected, and if there are large differences, it's a signal that something has changed. Well, we have to get through with the introduction here, and let's get our lingo in order here. A time series, an ordered sequence of data points over equally spaced time intervals. We see it many times in financial magazines. We can be looking at units or dollars. The analysis will extrapolate or project forward the past series into the future. To extrapolate means to extend the curve. It's more sophisticated than linear regression. Right over here, the word linear means straight line, and the forecasts here will include the seasonal ups and downs. We want to compare our actual results to those predictions. Large deviations signal a change in conditions, which could be fraud or errors. This fits in really well in a continuous monitoring environment. So, this is the purchasing car data. This is the chart from way back, I'm guessing chapter 2. And we have the monthly total expenses, and we saw that we had two storms over there. We saw that we had the excess expenses in the 9th month of the year. And indeed, the clever thing is, I believe that there was a government shutdown in that month, and so that could account for only half the expenses. So, what time series will do, it will forecast ahead, and in this case I've chosen to forecast ahead for 12 periods, and here it does, it has the forecast ahead, and what it's doing is it's taking these past patterns and extrapolating them forward. Minitab, my favorite for this analysis, and actually it's quite tame. It's a case of statistics, time series. This is my model of choice, decomposition, and indeed I have the old data here, and the projected, I'm just going to go back, the forecast is over here. This is reasonably painless to run. Now, we get lots of output, and what we're doing here, this is simply the linear trend over time. If it had to draw a straight line, where would that straight line be? And it's over here, and we can see that it's increasing. The blue is the actual, so we see these large peaks over here. The red is the best fitted line that it could. It will fit as best a line as it could, and it's trying to minimize the deviations between the actual and the fitted line. These are my forecasts. So these are the numbers going forward for the next 12 months that I would expect if these patterns held firm. But now we can see that we have some large differences over here, and this is measured by what I like to call MAPE, mean absolute percentage error. And over here what we can see is that this error is of the magnitude 0.14, which is 14%. So on average we're off by 14%, and so this is probably sort of, it's okay, but I'm not going to have all that much confidence in these projections over here. So when I look at 2015, these were the forecasts. You can see we have a higher expectation in September. These are the actual numbers, and in fact I have large differences. And there should be explanations for these large differences, and indeed the nice thing is that this might not have been apparent without this type of analysis. Let's have a look at some fraud data, and see whether we can actually do some time series analysis on this data. Catherine stole $509,952. And you would think that in order to steal $509,952, you have to be savvy, you have to know accounting, you have to be on your game, you have to be clever, you have to be technologically advanced. No. All she did, she worked at this little bank over here, she went into customers' accounts and she withdrew money and she kept the money. Victim, date, amount. This was her starting transaction, $44,000 out of this victim's account. And this is rather amazing because fraud schemes generally start small and then they get bolder. In this case, she started big and then thought, this is working, let me go. We can see that she likes round numbers and we can see that she likes big round numbers. I'm amazed. Look at this. August 22nd, 8,000. 2 days later, 7,000. I don't know about you, but if you gave me 8,000 on August 22nd, I'd make it last. I'd use coupons. I'd shop on sale. I'd look at the store brands. But at least I'd stretch that 8,000 a bit longer than 2 days. Joint account. We can see round numbers again. Joint account, round numbers. Like the round numbers, maybe she was paying a credit card bill over here. Love those round numbers. And indeed, this list is long. She stole $509,000. It took 2 years before she got caught. Here we go. Judgment in a criminal case. Embezzlement of funds by a bank employee. You will be amazed by this sentence. 1 day concurrently on all counts to remain in the holding cell till 5 p.m. That's it. But there's more. Watch this. A new indictment. A whole new indictment. Same Catherine. On the day she was sentenced, she told the judge, my brother and I were involved in an accident. My brother was severely injured. I took him home to live with me. He's on a hospital bed in my living room. I have to feed him, change him, and bathe him. It's not about me. My son will be put into foster care. I don't have parents. My parents are dead. The court is the judge. Okay, I don't want my brother to be put in a nursing home. The judge said she would take all these things into account. The statements were false. The brother had not been in a car accident, was not injured, was not living with her, and was not in a hospital bed, and was not being fed, changed, or bathed. He was living uninjured at home with his family. In fact, the way she was caught was that the brother the next day called the judge and asked what his sister's sentence was. The law clerk asked whether he was the paralyzed brother, and this was new to him. The parents were alive. In general, we don't lie about dead parents. When somebody tells you whether their parents are alive or dead, it means it. We really don't question it. Arrangements had been made for the child. A new judgment, corruptly influencing the due administration of justice, 70 months. And indeed, if we go to the federal sentencing tables, I think her sentence would have been 46 months for the original offense. And so 70 months is 46 months plus a whole lot of interest. Well, if we take the Catherine Harrell monthly totals, so here I get the blue is the actual monthly totals. The red is the best fitted line. This is the projection going forward. However, we can see the model is really struggling to fit a good line to this. The mean absolute percentage error is 44%, and so the conclusion that I would draw here is that it is highly unlikely that fraud data exhibits a nice time series pattern and that we can have a reliable estimate going forward. It just is not the type of data that is amenable to time series analysis. Look at this. The trend line is actually going down. Less and less. Could be harder and harder to find victims who don't notice 8,000 missing from their accounts. This is a nice case in the chapter. What I have here is grocery store sales. It's weekly sales, so you can see we peak on Sundays. And the blue, again, is the actual. The red is the fitted line. And it looks like just before the end of the data series, it's sort of mid-August over here, we have some huge activity happening here. Maybe it's back to school. And this is indeed data from a Mexican grocery store. However, this is my projection going forward, and this is my weekly trend. So it looks like Monday, Tuesday, Wednesday, Thursday are low days. Friday, Saturday, and Sunday are higher than average. Here again, we have the forecast. We have the actual. And of course, I'm looking at the actual with hindsight. And I can see the difference, and these differences are large. And so basically, this is what I would call a disappointing analysis. Something did change to make the actual numbers so seriously different from the forecast. Now, this is audit data analytics. And if you go to this link over here, the audit, you can simply key in AICPA Audit Data Analytics Guide, and you'll get there. What they do is they talk about the way that an auditor can use audit data analytics to identify ledger accounts that have had a large change in the balance. And so I made up this example. You can see sales go from 125 to 200. That's big. Cost of goods sold went up, doubled. That's big. And so what we would expect is, what I would like is some way to automatically identify these large changes here. But we know from the previous chapter that we can do that. We can use that vector variation score, and we can look at the contribution of a single line item, and we can see, well, we would see that these two ledger accounts contributed largely to the change in, to the overall change. So, the AICPA's Audit Data Analytics Guide discusses a general ledger application. The auditor wanted to identify unusual changes. If they found unusual changes, it would help them decide whether additional audit procedures were needed in the planned nature, timing, and extent of the risk assessment procedures. Sorry for jumbling my words there. The auditor basically just used professional judgment and said that an account would warrant further attention if the difference was $3 million or more. If I go back here, what we would be doing is something far more scientific and far more sophisticated. We would calculate the contribution, and it would tell us what a large contribution, which items had large contributions, and it would tell us how large the change was in the aggregate. So this is a real analysis that was done. And so what we could do is, this is just going back to chapter 10, the trial balance. We could turn this into two vectors, and what I would do is I would move these numbers over here so that I have a single column, move the credits here, and I would change this to negatives. And now I would balance down to 0 over here, but I would have a before and after with indeed these accounts, the credits, as negatives. And indeed, since we are looking at a change going from negative 20 to negative 23,000 is the same as going from positive 20 to positive 23,000. We're looking at the change. Here we go. So that example has only 20 general ledger accounts. I've seen companies with huge numbers of ledger accounts. This could be 80,000 is no problem, 100,000 ledger accounts. And what we would do is we would actually use this vector variation score to identify large changes from period to period. In fact, I've done that with a company, and we had some positive results with our pilot study. Now, this vector variation score, we can actually show it in a dashboard, and we can actually show it as a very special type of graph called a polar plot. And so now we are bringing analytic geometry into accounting. And so what we do is we have our two vectors, if you remember from the previous chapter, and what I'm going to do is I'm going to convert the the first vector, oops, I suppose that should be length. I should convert my first vector to a vector of unit length, and watch what's happening here. We actually have to do cosine, sine. I'm sure that brings back nice memories from trigonometry in high school. And what we're going to do is we are going to plot the first vector as a unit vector parallel across here with a length of 1. Then I rescale the second vector so that we're talking about the same units. And for Joe Biden's tax returns, this is the length of A when he was vice president. This is the length of B when he was not vice president. And we can see that we have a huge change in the length of B as compared to the length of A. And we include the angle theta over here. So this is an extreme change. If I go back to the example in the book, the customer rebates example, the first period is shown as a vector of length 1 over here. The second vector, there's its length, and here is the angle theta. So the bigger the angle, the more we have had a change in the internal dynamics of the numbers, and the larger the change over here, again, that simply tells us that B had a large change. In this case, I have two vectors of the same length, but that have a nice angle between them. So it's hard to sort of explain this in a time-tight video, but we can show these results as a polar plot. This is how I would do it. Not so hard to graph. I have to know what these things are, but once we've programmed Excel to do it, it's quite easy. So, running time series, I prefer Minitab, but SAS, the Rolls-Royce of data analytics programs, SAS has got plenty of routines. Here's proc procedure ESM, plenty of routines that will do time series, and indeed what it will do is exactly that. It'll give me forecasts, it'll give me confidence limits, it'll basically give me everything that I wanted. So SAS is the real winner. Minitab, an absolutely fine second choice. So we see time series graphs all the time. The dates are on the x-axis and the magnitude of the item under review is on the y-axis. What we want to do here is we want to predict the future values using the past as our guide, and the idea being that large deviations could be indicative of fraud or error. I can actually use this vector variation score quite well in this setting as well, and I can show the before and the after and the angle as a polar plot on a dashboard. And that is my review of chapter 11, and so bye-bye.